So here's now the theorem on this interesting direction in the bounded case. So let us assume that we start by a norm-continuous unitary group. So let me denote this by u of t, ut indexed by real numbers t. So this should be a norm continuous unitary group. On some Hilbert space H. Yeah, okay, let me again maybe write down what we really mean with this. So the UTs, so each of them is unitary. So U of t is unitary for each t. Then at 0, it's the identity. And we have this semi-group property, or this group property, that ut times us is equal to ut plus s. Or we have a representation of the additive group on R by unitary operators in my Hilbert space. That's what this is saying. So this should be true for all t and s in R. And then we also need to specify a continuity in t, and here we assume the strongest possible continuity. So namely, we assume that it's norm continuous. So this means that if t goes to 0, the norm of ut minus 1 goes to 0. Or ut converges in the norm to u0, the identity. And then the claim here is, if I have given such a unitary group, then there exists a uniquely determined Selfadjoint operator, which is the generator of this. So that u of t is is the exponentiation of this generator. So then there exists, and of course this is necessarily uniquely determined, Selfadjoint operator. Selfadjoint operator, and this operator is also a bounded operator, A of B of H. So my u of t, of course, will always be bounded operators because they are unitaries, so their norm is 1. But the question is about the operator, the generator. Is this bounded or not? And here, in this case, if I have this norm continuity, then actually the generator is bounded. So there exists such an A, such that the u's are given as e to the I ta. Good. Okay, so that's what we want to prove. And I mean, even the proof for this in the bounded case is not trivial, and it will more or less contain all the ideas which we will then be using and refining for the general unbounded case. Yeah. Okay, so what is the idea? The rough idea, of course, is that this A should be the derivative of my u. But of course, the problem is that I cannot be sure that the derivative exists. So one has to rewrite this in a way where this becomes maybe clear. So the idea is that my generator should be given as a derivative of u at the point t equal to 0. So I, or maybe A, or maybe I times A, should be the derivative of u of t at t equal to 0. Yeah, but I mean, I know that my u of t is continuous at 0, but I don't know whether it's differentiable. So a priori, I don't know that this derivative exists, and of course, the existence of this derivative should be encoded somehow in this semi-group property. In the same way as for the classical exponential function, I mean that the exponential function is differentiable at 0. And what also the derivative of the exponential function is, one can derive from this functional equation. Yeah, okay, so, but of course, we have to do this somehow, but we have to do this on a level of operators, and maybe there things are not so obvious. But in principle, we are trying to do what you are used to do for the classical exponential function. Good, so this is what we would like to do, but the existence of this limit is not clear. And we have essentially, we have to prove that this exists. Yeah, but I mean, instead of going directly into the u, actually instead of taking the derivative, we go the other way around. Namely, we do the integral. I mean, integration is a much smoother thing than taking the derivative, and there we can say much more. So a better way of getting the a is maybe if we do it the other way around. So a better way for getting the a is if we're integrating. I mean, if I'm integrating, so if I take the derivative of this guy, the a comes out. But if I take the integral of this guy, the a also comes out. Okay, the other way around, as 1 over a, but still I get an equation which should allow me to define the a, and to define it in terms of integrals, not in terms of the derivative. So the better way, and that is the one which we want to follow, is if I'm integrating my u's from 0 to t dt, so this should be, at least formally, so this should be 1 over I times a, and then I'm taking u tau from 0 to t. Just taking the integral over this function. This gives me 1 over the constant which I have here times my function from 0 to t, which is 1 over IA, and then I get here ut minus 1. Okay, so at least formally, I mean, I have to justify. This is just the idea how should I try to get my a. So I can get it from integrating my guy here, and then having it this. Or if I bring this on the other side, the I times a should be this times the inverse of this. Yeah. So this means that my IA should be, if everything is nice, it should be ut minus 1, and then I have to bring this on the other side, so the inverse of this guy. So times the inverse of the integral from 0 to t u tau d tau. But the inverse. Okay, so integrating is nice, but I have to take the inverse. So I have to think about whether the inverse exists or not. But this is something which is quite easy. Okay, and maybe if I want to, maybe let t going to 0. Okay, this guy goes to 0, which is not good. But what I can do is I can put a 1 over t here, and dividing by t here. So I'm just have, so here 1 over t and here t, so this doesn't change anything. But now the behavior of those two guys is nicer. In particular, this is also the limit which we would like to see. And in principle, you see, if t goes to 0, this quantity goes to 1, and then this quantity goes to the limit, which should be IA. So this is consistent with the idea of the limit. But we don't want, we want to take a limit at some point, but we want to take it at a point where we can see that the limit exists. So this here seems to be a good equation, and because we are going to use this, let me give a name to this without the inverse. I call this xt. This is a definition. So for each t, this guy here is xt. And so what do we have? I'm still doing formally, and then later I will prove this from the properties which I have. So this here, this is what I think IA should be. So it should be ut minus 1 divided by t times xt to the minus 1. And this should actually be true for any t. I mean, this is an equation which should be true for any t. So I can also do the same for another time, namely, let's say s. So it should also be the same as us minus 1 divided by s times xs to the minus 1. And now I can, this equal to this, I can get rid of the inverses by bringing them on the other side. So what I should have actually is that ut minus 1 divided by t times xs, bringing this on the other side, should be the same as this times this here. Us minus 1 divided by s times xt. Yeah, okay, so that's a good equation, because here we have now two variables, s and t, and we can, for example, now let t go to 0. Then we should get here our generator, and on the other side we might be able to see that the limit exists. Yeah, okay, so this is a good equation for starting, and that's actually what we want to prove. I mean, up to now I have not proved this, because I have just said, I mean, A should be this thing, but yeah, we were not really able to see that this is really the A which we want. But so what we want is this equation, and so now let us now really start from the beginning, defining everything, and then see that we have this and use this for getting everything we want. So now let me start by really defining the xt as I have defined it here. So this is 1 over t times the integral from 0 to t u tau d tau. So I'm starting from my unitary group ut, and then yeah, I'm just defining this guy here, and then of course the norm continuity of ut, so u tau, if tau goes to 0, goes to 1. So if t is very small, this is very close to 1, so it's essentially 1 times t divided by t. So this is very close to 1. And so of course it's very easy to check that the norm continuity of the ut gives me actually the continuity that xt converges to 1. So this gives me that the xt minus 1 goes to 0 if t goes to 0. And furthermore, this also implies that the xt, at least for small enough t, is invertible. Because you see, I mean, in this equation, I have to invoke the inverse, so I should know by some reasoning that this is invertible. But if it is very close to 1, I mean, something which is close to 1 in norm, and close means closer than 1, then this is invertible. So this means that x of t to the minus 1 exists as a bounded operator if I only make the t sufficiently small. So namely that this xt minus 1 is less than, let's say, 1/2 or so, because then I can make a power series expansion and I get that the xt is invertible. Okay, so this exists in B of h for t sufficiently small, maybe not for all t, but okay, we don't bother so much what happens for big T, but only if t is somewhere in the neighborhood of 0, and say, let's say for t less than t0. So we only do our arguments for times which are less than t0, so that we know that the xt is invertible. Yeah. Okay, and now I have defined my xt, and now I want to prove this star. So I mean, I should prove this star not from this reasoning here, but from the semigroup property of the use, because that's what I have. So I want to show star. So for this I take 2 times. So I want to show star. So I'm taking times, and let's say I'm taking them s and t. Let's say, yeah, maybe say s smaller than t, just to be definite, and smaller than t0, so that I know that xt and xs are invertible. And let me take them on this side. And so, I mean, if I want to go for the limit later on, I should take the limit t goes to 0. Of course, I should be bigger and smaller than 0. Here I restrict to bigger than 0, but on the other hand, I mean, yeah, this doesn't matter, because by the semigroup property, I mean, I know that everything on the positive side, I can move to the negative side, and I get the same kind of results. Good, but anyhow, so what do I want to see? I want to see that this ut minus 1 divided by t times xs is the same quantity if I just exchange s and t. And maybe here I just leave it open, which is the bigger and the smaller one. So let us see how could we get this. So ut minus 1 divided by t. I'm multiplying this with xs. And I want to see, I can write it in a form where I see that it is somehow symmetric in t and s. And so, yeah, let me just use the definition of xt. So ut minus 1 divided by s. I'm not changing this. And then I'm writing the definition of xt, or xs now. So this is 1 over s times the integral from 0 to s u tau d tau. Okay, and you see, I mean, I have here s and t. That's good, that's symmetric. But of course, the other things look unsymmetric. And let us see what they really are. So I have here 1 over s times t. Then I have here the integral from 0 to s. And now, of course, I multiply this here inside the integral. So I get ut times u tau minus 1 times u tau. So I have here ut u tau minus 1 times u tau integrated with respect to tau. And of course, now the semigroup property tells me that this ut times u tau, this is ut plus tau. Yeah, and now you're seeing what am I doing here? I'm integrating my u's from some initial time to some end time, because here I'm starting at 0 plus tau and I'm going up to s plus tau, and here I'm starting at 0 and I'm going to s. So what I have here, maybe let me draw. Let's say I have here 0, I have here s, I have here t, and I have here s plus t. Then I'm integrating here over my u, and I'm integrating in this term, I'm integrating from 0 plus tau, no, tau is 0, so from t plus 0 plus until t plus s. So I'm integrating from t to t plus s. So I'm integrating this here with a plus sign. This is this integral. And then I'm subtracting the integral over, again, over the u's, but now from 0 to s. So I'm subtracting this integral. Okay, so this quantity here is the integral over the u from here to here with a plus sign, and from here to here with a minus sign. And now I'm claiming this is the same as when I'm exchanging s and t. So let me do this. So this is what I'm claiming here, but we have to see that if I exchange here s and t, nothing happens. Here, of course, I'm integrating now from 0 to t, and here I have u s plus tau minus u tau. So this is the same quantity as here. I just have replaced s by t and t by s. And I'm claiming that this integral is the same. And of course, a priori, I mean, this integral is not the same as this, and the integral over this is not the same as this, but I'm claiming the effect, total effect, is the same. Because what am I doing here? I'm integrating over the u's with a plus sign from where? From s plus 0, so from s up to s plus t. So I'm integrating from s up to s plus t with a plus sign, and then I'm subtracting the integral from 0 to t. So I'm going here from 0 to t with a minus sign, and now you see, I mean, this is not the same as this, and this is not the same as this, but the sum of both is the same, because I'm going over this with a minus sign, I'm going over this with a plus sign, and then I have here additional terms, but they're cancelling away, because this is the same interval over which I'm integrating, but here with a minus and here with a plus sign. So this cancels away, and the net effect is the same in both cases. And so this here is now really, this is this here where I just have exchanged s and t. So this is the same as u s minus 1 divided by s times xt. And this is our equation star. So I mean, this definition, this follows very nicely and easily from this semigroup property. Here I have used the semigroup property. Yeah, okay, and now we should now see whether we can use this. So first of all, we can now use this to define our generator by taking the limit. So yeah, we have now this equation here, and now I can take the limit. So let's say I let one of the two variables, two times, go to 0. Let's say t goes to 0. Then this goes, or maybe let's take s goes to 0. Then I can control this side very easily, because this is constant. Nothing happens, and xs has a very nice behavior. I know if s goes to 0, this goes to 1. So I can send s to 0, and I know that this side has a limit, which means the other side must also have a limit. Okay, but what is the limit? I mean, what happens here if s goes to 0? Here is nothing changes, and here this is exactly the limit which I want, which should be I times a. So this means this equation here, this is true for all t and s sufficiently small, so it is, I can also take the limit if s goes to 0, and I know on this side the limit exists, so it must exist on this side. So this is the argument which gives me the existence of the limit. Okay, and then this allows me to define the A and check more or less all the properties. Yeah, so let me continue here with this. So I take star, which I have proved for at least s and t small enough. And now I send s to 0. So now fix t in star and send s to 0. Okay, and we should note that we know what happens with xs if s goes to 0, namely this goes to 1. So this is a limit which we can control very easily, because this is about the integral. And integrals are easy to control. But putting this together tells me that if I can control the integral, I can also control the derivative. That's the nice thing which I have here. Yeah. So then I have, let me write it again, I have ut minus 1 divided by t times xs is the same as us minus 1 divided by s times xt. I just have written down again my equation, and now I'm sending s to 0, and this here converges then. Here nothing happens because this t is just fixed, divided by t, and this here goes to 1, and on the other side, yeah, on the other side, this here then also has to have a limit. This side has a limit, so this side must have a limit, which means that this guy here has a limit, and this limit is exactly given by this side times the inverse of this. So this here tells me that ut minus 1 divided by t, the limit on this side must be the same as the limit on the other side, where s goes to 0, of us minus 1 divided by s multiplied with xt. So in particular it shows me that this limit exists. Yeah, and now now what? Now this limit exists, so let me call it, I can give a name to it, and I call it IA. So A, and okay, as we know it's good to have an I there. So I can define it like this, and then you see that I have here defined the A. Well, it is this limit, but by this equation it is also, it is this times xt to the minus 1. And we know that t is invertible for t small enough. We are only doing this for small enough t, then I can bring it on the other side. And so I get here that this I, A times xt is the same as ut minus 1 divided by t. And this I have for all t, at least for t small enough. So I have defined the A now, it's this limit here, but it also satisfies this equation, and this equation is true for all xt's. So I have this here, and this gives me now, if I write this in the right form, this gives me exactly the relation between u and a in this exponential form. So let me also do this. So now we are done. We have now defined the a, and we have found the relation with the u's, and this contains everything. We just have to work this out. Yeah, so what do I have? I have this guy here, and let me solve yeah, solve this for the ut. Multiply it with t here and bring the 1 also on the other side. Then this tells me what I have here is that the ut is equal to the 1. And then I have plus plus IA xt. Yeah, maybe I write it down. So this is 1 plus IA t times xt. But the t times xt, this is this integral. So the xt was 1 over t, this integral. So if I multiply it by t, I'm getting the integral. So what I have here is 1 plus IA. And this here is the integral from 0 to t u tau d tau. Yeah, okay. And of course, this is now not yet ut expressed in A, but it's somehow the germ for doing it, because the ut appears here again, and I can plug this equation into itself and generate in this way actually an exponential power series expansion here. So namely, let me see. Yeah, let's do the first step. So what I have here, I take this equation. I have 1 plus IA. I'm integrating from 0 to t. And now for the u tau, which appears here, I'm just plugging in this equation again. So the ut was 1 plus IA. And now I have to integrate over a new variable from 0 to tau, because I want the u tau here. And I'm integrating over, let's say, u sigma d sigma. And here the d tau. So what I have plugged in here is just the u tau according to this formula again. And now you see I have here the start of the exponential series. So I have 1. Here I'm integrating the 1 from 0 to t, which gives a t. So I have ITA. And then I'm left with this integral. So here I have I times I. AA, so I have IA squared, and I'm integrating now this u sigma d sigma d tau. So you see I have here I had the 1, or here I had the 1, and the rest which involves u tau. If I iterate this once, I get the 1 plus ITA, and then I get a rest which involves tau. But again, which involves the u's. But again, I can plug in this equation here, and then I get a next step in the exponential function. So namely then, maybe I'm doing it here. So what is this now? If I'm plugging in here, again, this formula above, I have here the integral, and then the u sigma is now 1 plus I times A. And then I have the integral from 0. I have to go to this sigma here, and I need a new integration variable. Maybe I call it tau. Maybe. No, tau is already used. Let me call it nu. So I have the u nu. So this is integrating this. And then I have this d sigma d tau. Yeah, and you see again I have a term which I can integrate, namely this 1 here. So this gives me this integral here over this 1, and I'm integrating here. So maybe I'm integrating from 0 to t. So the tau is between 0 and t, and then the sigma goes from 0 to tau. So I'm integrating from 0 to sigma to tau to t. So I'm integrating here sigma and tau ordered between t, and this gives me exactly, if I'm integrating this over 1, this gives me t squared over 2. So I'm integrating not over the square, but only over half the square, because I have this order. So this gives me here a t squared over 2 plus, okay, a threefold integral over u nu, this d nu, d sigma, d tau, where I'm integrating here over 0 less than nu less than sigma less than tau less than t. And if I'm integrating this over 1, I get t to the power 3 divided by 3 factorial. So I get via iteration, I get from this here really the exponential series for my operator A. So this here by iteration. And of course, checking that this here really converges in the end. I mean, the remainder terms are getting smaller and smaller. They go to 0, and I really, I'm only left with all the terms which I get in this iteration procedure here. So this gives me that u of t is the sum over from n0 to infinity of iat to the n divided by n factorial, which is, as we know, nothing else than e to the ita. And that's what I claimed. Yeah. Okay. And then, of course, you can check all the other properties. So, in particular, you can check that u to the minus t is the same as ut star, and this implies that this a here is really a Selfadjoint operator. If you just maybe go back to this here, if you take the adjoint here, then you see taking the adjoint here gives you a u s star, which actually is a u minus s, and then you take the limit with a minus s, and this gives you here the exchange, and so in principle from this you see that a is Selfadjoint. So a is also Selfadjoint, and so you get all the properties which I'm claiming here. Yeah. Okay. So maybe a few details are still to check, but the main argument I think I have presented here.